When an unstable isotope decays, it's possible to work out exactly how the nucleus will change if you know what type of radiation is being emitted. Today we're going to look at the nuclear decay equations for alpha and beta. Let's start off with alpha. So remember that alpha is made of 2 protons and 2 neutrons. That means we could write its symbol just like an element's symbol. So I'm going to write alpha, and I need to work out the atomic number, which is the number of protons, so that's going to be 2, and the mass number, which is the total number of protons and neutrons, which is 4. Cool, so there's the symbol for alpha. Now you might notice that this is actually the same as a helium nucleus. And you're right, sometimes people actually write helium instead of the alpha symbol. It doesn't really make too much difference. I'm going to stick with alpha just so that we can remember that we're dealing with alpha decay here. But if you ever see it with helium in place, it's exactly the same. Don't worry about it. Okay, I'm going to look at the alpha decay of uranium-235. Uranium-235 has a mass number of 235 and it's got an atomic number of 92. Now, don't worry, you're not expected to remember the mass number and atomic number of elements by heart. You'll be given a periodic table or something if you ever need to know that. Okay, so we've got this uranium here and we know it's going to undergo alpha decay. So how can we work out what's going to be left over? Well, I know that the nucleus is losing 2 protons and 2 neutrons. So let's work out how those numbers would change. I can actually use these numbers that I've got written in front of me. I've got 235, and I know that because of the alpha particle, that's going to go down by 4. So 235 take away 4 is 231. Can do exactly the same thing for the atomic number. We started off at 92, and the alpha particle is taking away 2 from that, so we're going to end up with 90. I could then look at a periodic table, find the element that has an atomic number of 90, turns out it's thorium, and there you go. That is a decay equation for uranium-235 undergoing alpha decay. And you can do that with any atom you want, really. Just as long as you remember that the symbol for alpha is a mass number of 4 and an atomic number of 2, and you can work that out just by remembering 2 protons, 2 neutrons. Nice and easy. Just as an aside, whenever we deal with nuclear decay, the thing that we start off with is called the parent nucleus, and the one that we end up with is called the daughter nucleus. All right, beta decay is a little bit more complicated. Remember that beta is an electron, but we're dealing with nuclear decay. We're dealing with the nucleus. There's no electrons in the nucleus, so what's going on? Well, in beta decay, a neutron turns into a proton and an electron. So the number of neutrons in the nucleus is going to go down by 1, and the number of protons in the nucleus is going to go up by 1, and the electron gets kicked out as beta decay. Now there's a clever trick that you can use to remember that it's a neutron becoming a proton and not the other way around. All you've got to remember is that the universe likes harmony. The universe loves to stay balanced. Beta decay is an electron. An electron has a negative charge. The universe does not want to produce a negative charge without balancing it out, without also producing a positive charge. So that's how you remember that a proton is being produced here. We end up with a negative electron and a positive proton, nice and balanced, neutral overall, because the positive and the negative cancel each other out, sort of. And we started off with neutral, a neutron as well. So the universe stays nice and balanced and in harmony. Okay, so let's see what that would look like as a decay equation. This time I'm going to use carbon-14 as my parent nucleus. It's got a mass number of 14 and an atomic number of 6. So let's work out what we're going to be left over with. Well, the atomic number is the number of protons. I've created a proton, so the atomic number is going to get 1 bigger. That's going to be 7. Okay. What about the mass number? Well, the mass number is the number of protons plus neutrons. We had a neutron becoming a proton. So in actual fact, the overall number of protons and neutrons isn't going to change. It's going to stay the same. It's going to be 14 in this case still. Okay, and I can look up on the periodic table. It turns out this is an isotope of nitrogen. So there you go. But now I'd like to fill in this symbol for beta as well. Well, the mass number is easy enough. I can see that the mass number didn't change. 14 plus what equals 14? 0. So we're going to put a 0 there. But the atomic number is a little bit more complicated. I can see that it's got one bigger, so I need to figure out 7 plus what equals 6. And the answer is -1. So for the atomic number for beta decay, we write -1. This is a little bit weird and counterintuitive because you might be thinking, well, it doesn't have -1 protons, but we just want to make these numbers all balance, basically. So there you go. That is what the decay equation for beta looks like. Now, gamma is a little bit different. We're not going to go through that in this video. Just make sure you remember these two symbols for alpha and beta decay.